Did it. Okay, so guys, here we go. Today is actually kind of a really interesting day. You're going to enjoy this, but today is going to be enjoyable and sort of intriguing. It's also got to be a part of the bigger picture, right? So guys, let's remind ourselves where we're going so that you understand how this all fits in. So guys, last time in lab, what did we do? Fire. Yes, the flame test lab. But guys, you need to understand and remember this. Why did we take these metal atoms and not light them on fire, but add heat to them with a flame? What did we experience? Color change, light, right? And so guys, you got to get this or this isn't going to make sense to you today. What does light and colors of light have to do with atoms and electrons? Where's the connection? I know it's early. Okay, so let's remind ourselves. Hold on, I'm going to model this for you. Okay, so this is an electron, ready? And this electron, do you know the connection? Go ahead, tell me about it. And use the words, if you can, that you learned last time. Here we go. Okay, so we've got an nucleus in the middle, right? We've got an electron and it's in its ground state. When we add energy, and it could be heat or anything else, now it's in an excited state. It can't stay there. And? Good heavens, you said that way better than I could have. And so depending on how far it falls, we see different colors of light. What do we see for short falls? Red. And longer falls? Blue, violet. And is it all coming back to you? Okay. So guys, with that then said, that is whose model of the atom? Bohr's model of the atom. Okay. So yes, and that's the point. Guys, last time in lab, we built up the Bohr model of the atom. Today, we're going to tear it apart. So guys, you are going to walk out of here today going, I'm really not quite sure what atoms look like anymore. I know it's not the Bohr model. I know why it's not the Bohr model, but I don't know what it is. So guys, the way that this is going to go down then relative to your notes is this, and just trust me on this. There's going to be a lot of stuff up on the screen. If it's not on here, don't write it down. So guys, you'll notice that this sort of changes from something sort of like notes in a table to an outline, right? Here's the way that this goes. Everything from the middle hole punch up is tearing the Bohr model apart. Okay, so once you've got this top table filled out, you will understand why the Bohr model's busted. Then guys, everything below the hole punch, the outline, is simply going to be the stuff that you need to know to replace the Bohr model, but we're not going to do that till Thursday. Get the idea? Okay, so whose is this? Is this mine? Oh, I thought I stole one of yours. Never mind. Sit. Okay, so guys, again, then the idea, kill the Bohr model today, replace the Bohr model on Thursday. It's a magic day. Then guys, Monday, we're going to refine what you learned on Thursday, and then Wednesday is the test. Got it? All right, so guys, here we go. Let me get rid of this, and let me grab this. And once again, guys, please do not write it down unless it comes up on the screen. So, leading you through what we just talked about, it goes like this. Guys, we come back to this familiar idea, and when we introduced this again relative to the flame test, we said we are going to build up the Bohr model. And again, you guys all just talked about the idea of ground state, excited state, falling electrons in light, right? Okay, so, but we also understand that we're going to kill the Bohr model today and get rid of it. So guys, in order to do that, right now what we're going to do is build up this Bohr model just a little bit more, and then we're going to understand why it didn't work. So guys, the conversation goes like this. You may remember that when we started remember the videos that we watched? Do you remember those? And did we do 2 or 3 of the Hank Green videos? We did 2 Hank Greens and then that crazy video, right? And so guys, remember the purpose of those videos was just to create confusion. So we knew about the Bohr model. We know that we're now going to replace the Bohr model. And you may remember in one of those Hank Green videos, right, we talked about orbitals. And you may remember these came in fast. He was like the S and the P and the D and the F. And he was talking about these ideas. Well, guys, what you're going to find out is this is how we're going to wrap up the day. So we're going to kill the Bohr model. We're going to start to flirt with some of this stuff about orbitals and S's and P's and D's and F's. But we're going to do a deep dive on Thursday, and it's all going to make sense. Okay, but guys, in order to make the connection, do you remember this video? The very last video? Do you remember what this guy was talking about in those really soothing tones when this part of the video came up? Do you remember what he was doing? And he was saying an electron can be here, and then it goes there without traveling through the space in between. Or the electron can go from here to there, traveling through all the spaces in between. And an electron can appear where it never was before. Remember all that crazy stuff? And disappears and reappears. So guys, here's the overview of the day. We are going to understand that electrons are not like little planets moving around the nucleus. We are going to understand that they're way wackier than that. We're going to touch a little bit on S, P, D, and F, and then we're going to call it a day, and we're going to wrap this back around on Thursday and figure out what's really going on. You get it? Okay, so guys, building up then the Bohr model of the atom. Here's the way this goes. But guys, you'll notice that this is not in your notes, so don't write it down. So the big picture is this. Guys, today what we're going to do is 2 things. We are going to figure out why the Bohr model is incomplete, and we are going to gather the information that we need to replace it. But we're not going to replace it. All we're going to do today is get the pieces, well, as it says here, we're going to get the pieces for the new model, but we are not going to completely build the new model. We're just going to give you the building blocks. And guys, where are you going to write down those building blocks? In the outline down at the bottom. Get the idea? So guys, when you come into class on Thursday, I'm actually going to have you break out your notes from today, and we're going to take that outline and we're going to rework it and have some pretty neat aha moments. You guys ready to go? All right, here we go. So guys, Bohr model first. And again, this is not in your notes, but it goes like this. We understand that Bohr developed his model by studying light. And the idea then, the connection, is that Bohr, just like we said, is trying to study electrons like particles moving around the nucleus, like planets around the sun. He knew that these electrons would rise, they'd fall, they would release light. But guys, all of this required that he describe electrons like little particles. Now guys, if you're going to do that, if you're going to make a model that describes a thing as a particle, in order to develop the model, you've got to be able to track that particle. You've got to know where it is, and you've got to know where it's going. And guys, this is the problem that Bohr started to run into. But before we talk about the problem, we need to talk about one thing about Bohr's model that you're going to find out did last. So here's what Bohr did. He said, I know that these electrons are in orbits, and these orbits have sizes and capacities. And this is going to feel familiar. Here's what he did. He said, here's the nucleus of an atom. Here is this first orbit. He called this thing orbit 1, or n is equal to 1. He used a variable to describe it. He said, this is n equals 1. And do you guys know this? There's 2 electrons in the first orbit. Did you guys know that? That is actually true. Now, so guys, he also said something interesting. These orbits don't have unlimited capacity, and I think you know this too. So guys, if we want to put a third electron in this atom, can it go in the first orbit? It goes in the second. And guys, did you know this? That there can be 8 electrons in the second orbit? Did you know that? Probably from biology. So we've got the second energy level. There can be up to 8 electrons in that energy level. Just so you're connecting, 2 plus 8 is 10, and that would make this neon. Now guys, what if we wanted to add an 11th electron and make this sodium? Could that extra electron go in the second ring? It can't. It's got to go in the third ring. And guys, this is the fundamental of the Bohr model. You've got orbits. You put electrons in the orbits. Eventually you need a bigger orbit, and they just get bigger and bigger and bigger. You get the idea? Okay. Now guys, how did Bohr know where these orbits were? Well, he did that by looking at the light. And so he said, if I could take an electron from the first energy level, kick it up, let it fall back down, he could study that light, figure out the distance between the orbits, and that helped him build his model of the atom. Get the idea? Now we're going to tear it apart. You ready? Guys, here's what happened. 1917-ish. Bohr is gathering light, studying atoms, looking at what electrons are doing. And guys, this worked really, really well with simple atoms like hydrogen and helium and lithium and things like that. But here's what happened. As Bohr tried to take this model and make it apply to bigger and bigger and bigger atoms, he started to get really weird data. Like all of a sudden, his data just totally didn't make sense. So guys, what do you do if you're a scientist and your data gets crazy? What do you do? This is an important question. Some of you are going to be scientists, and you're going to be in a lab, and you're going to be collecting data, and your data is going to get weird. So guys, if you start getting weird data, what's the first thing you do? Stop. And then what? Do it again. Guys, if your data's bad, the first thing you do is you go back to your experiment and you make sure that everything's set up right, and then you repeat it. Many times that will fix your data. But guys, Bohr did that, and his data was still messed up. So what's the second thing you do if you've got bad data, but you know your experiment's not wrong? What do you do now? Actually, that's exactly right. Guys, you share it. You take that data and you publish it. Right now, that happens instantaneously on the internet. In 1917, he wrote a paper, and he shared this paper with a lot of really bright people, including Schrodinger, Einstein, a guy named Heisenberg, and that's exactly what Bohr did, is he said, hey, you really smart people, look at my data because this doesn't make any sense. And now you've got a lot of really smart people looking at your data. And guys, this is the cool thing that happened. When these smart people started to look at Bohr's data, they actually came back, and the first thing they said was this: your experiment is not broken. And that was a relief to Bohr, because he was afraid that it was just his data collection that didn't work. But guys, and this is where your notes are going to pick up, it was the next thing that happened that was significant. And it all has to do with what's called the Heisenberg uncertainty principle. See it in your notes? So guys, this is the way this went down. Bohr is going, hey, yo, my data's screwed up. And everybody that's looking at it is going, no, your experiment's okay. And then Heisenberg took Bohr's data and said something really important. He said, Bohr, your experiment's not broken. The problem with your experiment is electrons aren't particles. It was actually Heisenberg that suggested that. And here's how Heisenberg knew. He knew that in order for the Bohr model to work, you needed to be able to track electrons like little particles. And what Heisenberg did in reanalyzing Bohr's data is he realized that is a fundamentally incorrect way to understand electrons. That electrons are untrackable. And the reason that they're untrackable is because they are not particles. And so here's the way Heisenberg said it. He brought up this idea of uncertainty. And guys, what does it mean to be uncertain? You're just not sure. But what are we not sure of? And this is the important point. Here's Bohr tracking electrons like particles, right? And it's not working, and his data gets weird. And Heisenberg comes back and says, Bohr, it's okay to be unsure or uncertain about where these electrons are. And the reason that it's okay to be unsure is because electrons aren't particles in the first place, and as a result, you can't track them. Does that make sense? So guys, here's the way Heisenberg said it. And this is what you want to get in your notes. He said, we can't know exactly where an electron is and where it's going. He said, you're okay, Bohr. I understand that you're trying to track electrons and it's not working. Well, guess what? The reason it's not working isn't because you are screwing up. The reason it's not working is because electrons aren't particles. And because they're not particles, you can't treat them as such. And when you try to study them that way, you're doomed to failure. So guys, it's important you understand this, that the breakdown in Bohr's model was not that he wasn't doing good science. The problem wasn't with his experiment. The problem was something fundamental about electrons. That fundamentally Bohr's research was destined to fail. Not because Bohr was a bad researcher, but because electrons are fundamentally untrackable. You can't figure out where electrons are and where they're going because they aren't like little planets moving around the sun. You get the idea? Because guys, we just did it. We just killed the Bohr model. So, who killed the Bohr model? Heisenberg. Yeah. Heisenberg came along and said, Bohr, your model is destined to failure because it's treating electrons like little particles, and they're not like little particles. How do we know they're not like particles? Because they won't allow us to track them, and that's why Bohr's data got weird. You making all those connections? Does that make sense? So guys, what happened next? So now we know the Bohr model's busted. We know that thanks to Heisenberg, who interpreted Bohr's data and told us that electrons are not like little particles, and as a result, we can't study them as such. So what happened? You guys remember reading about this a little, well, sort of. We talked about it. Do you remember what happened next? Say it again. Yeah, so guys, in steps Schrodinger, right? And guys, think about this progression of thought. So Bohr's doing these experiments, treating electrons like particles. Heisenberg says, knock it off. And guys, before Schrodinger stepped in, there was a crisis in atomic research. Like seriously, all these research labs were like, what do we do? We always thought electrons are particles. Heisenberg just showed us they're not. We don't know where to go next. What is another experiment that we can do to figure out what electrons are doing if they're not particles? Because if electrons aren't particles, we can't do experiments. So what did Schrodinger do if he didn't do experiments? Do you remember? Exactly. What kind of stuff did he write down? Math. He did equations. And guys, that was the thing that was cool about Schrodinger. He said, that's fine. Heisenberg, if we can't treat electrons like little particles because they're not, let's stop trying to study electrons in lab and let's actually see if we can describe them mathematically with equations. And guys, this is where we're going next. In comes our good friend Erwin Schrodinger, and he saves the day. And guys, the way that Schrodinger saves the day is by suggesting this idea, and this is in your notes, of probability. And guys, this is the way the concept goes. You ready? Follow this through history. So Bohr, electrons and particles. Heisenberg, knock it off. Now they don't know what to do. So Schrodinger steps in and says, let's not worry about treating electrons like little particles because Heisenberg said it doesn't work. So here's what Schrodinger said. He said, if we, and note, guys, this is going to be a subtle little word play. Don't miss this. So Schrodinger said this. He said, if we can't know where electrons are or where they're going because they're not particles, what if instead of worrying about where they are all the time, what if we start to think about where they will probably be most of the time? Do you see the subtlety there? Because guys, if you're studying electrons like particles, you've got to know exactly where they are. But if you start to think about electrons differently, then you can just worry about where they will probably be most of the time, and that we can describe with math. So guys, the idea with probability, and this was Schrodinger's big idea, that instead of tracking them like little particles, which Heisenberg said doesn't work, Schrodinger came along and said, what if we actually think of them differently? What if we just worry about our ability to figure out where they will be most of the time? That's the idea behind probability. Now guys, in a second, some pictures are going to come up on the screen. Don't try to draw them. There are a couple more things to write down under probability, but hold on just a second. Don't try to draw these pictures. So guys, here's the question. How did Schrodinger figure out where the electrons would probably be? How did he do it? What research did he do? He didn't do anything in lab, right? What did Schrodinger do? Math. Guys, that's how Schrodinger figured out where the electrons would probably be, is by using mathematical equations to figure out what they're up to. He didn't do any laboratory research. He used math to predict where these electrons would be. And interestingly, the equations that he used were the same equations that physicists use to describe waves. And guys, here's what he did. He started to take these equations and use them to describe where electrons would probably be. And he started to think of electrons like this. He started to think of electrons as probabilities. Now guys, it's important you understand what you're looking at here for this idea of probability to make sense. So guys, what does this heavy black or blue dot in the middle represent? The nucleus, right? And so what do those lighter blue dots represent? Not electrons. One electron. Now guys, if this doesn't make sense, think about it this way. What I want to do is I want to explain to you, show you visually what this diagram on the left represents. So guys, do this with me mentally. So let me make the room as dark as I can, and let's see how we're doing. Okay, that's where we want to be. All right, so guys, strobe light, right? Okay, so here's the idea. What are you looking at when you were looking at that image on the left? Well, guys, the idea is this. So here's our electron, right? And imagine that my tabletop is a piece of photographic film, and we've got this light up here, and imagine that we could put one atom between the light and the film on the tabletop. Now, guys, and then imagine that this electron is moving through space. Got the nucleus. We've got this electron is moving, but every time the light flashes, it casts a shadow. And imagine that that shadow was actually imprinted in the film. So, if the Bohr model of an atom was right, and if this electron was actually moving in a circular orbit around the nucleus, if we allowed this picture to develop for a little while, eventually what would we see on the tabletop if we developed that picture? A circle, right? But guys, that's not what we understand electrons are doing. So now connect to that fourth video that we watched the other day. Guys, what are electrons doing? How do they move? Do they move in regular orbits? No, this electron can be here, and it can appear over here, and it can jump to there, and it can move randomly, and it can go, hey, I'm over here, and now I'm over here, and then I'm in all places at the same time. But guys, it's chaos. So imagine chaos. Wah! The electrons are just going bananas, right? Well, guys, if you were to develop that piece of film, what would that piece of film look like? Can you see that it would look like this? Do you get the idea? But guys, understand that it is not completely chaotic. What do you notice about the dots? They're closer together near what? The nucleus. And so, guys, what Schrodinger was finding was that there are, notice the word, there are places where electrons will probably be, and there are places where electrons will be very unlikely to be found. So there are places of high probability, and there are places of low probability. And he said that these places where electrons will probably be are really the way that we need to understand electrons. Now, guys, this is where this gets a little bit weird. You ready? So, thinking about this picture on the left, imagine if, imagine that we allowed this to continue to develop over, I'm going to hurt myself. I should take off my watch. Imagine that we allowed this picture to develop over enough time and we made a whole lot of dots. Guys, eventually, what is this piece of film going to look like? What do you mean by covered, Enoch? What are you thinking? But really everywhere? Go ahead, Austin. No, I totally understand what you're saying, and I think that's, Enoch, what you're getting at as well. And here's the thing that's interesting. These probabilities do actually go to zero. There are places where you will not find those electrons. And there are also places where you will most likely find those electrons. But there are, in fact, places they won't be. And we'll talk more about that on Thursday. Go ahead. Yeah. That's brilliant. And so are there, if we've got, because we understand this is one electron. What if there's 50 electrons? There are still places they won't be, and there are still places that they will be. And guess what those places look like where they will be and won't be? They look like this. That's what these are. These are the places where they will and won't be. And there are still places in there where the electrons will not be. Yeah, crazy, right? Go ahead, Austin.
So, with 2 electrons,
I love you guys. Keep going. What? Yeah, and I'm sorry, I cut you off. Finish your thought. Right, and the answer is they can't. There's a rule for that. It's called Pauli exclusion principle. The Pauli exclusion principle says that 2 electrons cannot be in the same place at the same time. It's a mathematical concept, but that's the application of it. They can't be in the same place at the same time. Yeah, okay.
So since they're all the same charge,
yeah. Good. Yes. What's your thought with that, though? And that's exactly what happens. Without a strong nucleus, and that's exactly what's going on. What we're finding. So maybe a bigger question is, why do the electrons take on all these crazy shapes and spaces? And the answer is because they're trying to get as close to the nucleus as they can and as far away from each other as they can, and that's the best way to do it. Yeah. So. You guys are amazing. Here's the it's not exploding, it's not running into each other. Yeah. But guys, here's the thing. All of your, I guess we could go to Thursday, because every single one of your questions, I know that I tried to answer them, but those 4 questions that just came up, every single one of them is going to be answered in great detail on Thursday. Thursday's a really cool day. So guys, do you understand what we're looking at here? We've got these electrons, they're moving chaotically around the nucleus. There are places where they will be, there are places where they won't be, and this is coming back to our thought a second ago. Is this still on? Oh, good. So guys, the thought then is that if we allow this to develop over a greater amount of time, again, eventually what are we going to see? And I wonder if you would agree with this. Eventually, we would see this. Do you see what I'm saying? That if we had enough of these dots, but remember that doesn't mean a lot of electrons, that means one electron moving through space over time, eventually these dots would make this volume appear solid. Do you see what I'm saying? Now guys, this is important because that is actually how we think of electrons. When we think of electrons as a chemist, we think of electrons as being large, solid entities, if you will. We don't think of electrons as being these little points in space. We think of these electrons as occupying large, three-dimensional spaces. And now you're going, wait a second, does that mean that an electron is this big old ball? The answer is absolutely not. An electron is still a point, but that electron behaves as if it's a big old, in this case, sphere. So you're going, wait, back that truck up. That can't be. I know that if the nucleus of an atom is the size of a marble, then the atom is the size of Lavelle Edwards Stadium, and it's mostly empty space. You already told me that. And now you're telling me that electrons actually act as if they're big old spheres, when in fact we know atoms are mostly empty space, and these electrons are itty-bitty. And guys, I would say to you, yes. No, yes, but yes. And it's really not as crazy as it seems. So here's what I want to convince you of. It is not crazy to think that an individual point like an electron can behave like a big old solid sphere. It's not that crazy. Guys, let me show you what I'm talking about. We're going to use this fan to represent what I'm talking about. So guys, if this fan is going to be our model of an atom, where's the nucleus of the atom? Where's the nucleus of our fan atom? Right there in the middle, right? So guys, if we're going to say that this fan is an atom, what then are the fan blades? The electrons. Now guys, understand that this is not a totally great analogy, because when I put these electrons in motion, this isn't the Schrodinger model, is it? Whose model says they go around in circles? That's the Bohr model. If you're looking for a Christmas gift for me, see if you can find a fan where the blades move chaotically around the nucleus, going in and out of existence like electrons do. That would be a great Christmas gift. But guys, you understand what I'm saying, right? This is not a perfect model of an atom, because these electrons do not move around the nucleus like planets around the sun or fan blades around the center of the fan. They should be moving chaotically, but they don't make that kind of fan. So here's the idea. I want to demonstrate to you that this atom has space in it, okay? So I can take rubber bands and I can shoot them through the empty space inside this atom, right? You would agree that I'm demonstrating to you that, in fact, atoms are mostly empty space. But, no. If I put these electrons into motion, and again, they should be moving chaotically, but we can't. Guys, do you see what just happened? Now watch what happens when I try to shoot rubber bands through the fan. Now, this atom, I'll get out of the way. Oh gosh, that was really sad. Sorry. It was a small rubber band. I couldn't get a good grip. So guys, you'll notice now that I am shooting at the same empty spaces that exist within these fan blades, but now all of a sudden this thing's behaving as if there's no empty space. So for all intensive purposes, this thing is now behaving as if it's a solid, when we know from experience there's actually space in between. Guys, that's like electrons. Are electrons individual things? Yes, but they don't behave that way. Why not? Because they're moving. But guys, it's not that radical of a concept, because you can see here, you know that these fan blades still exist as individual blades, but they behave as if they're a big old space simply because they're in motion. And guys, electrons behave exactly the same way. Yeah.
So it's like there's a shell like around.
Exactly. It creates...
But there's still like all the empty space.
Absolutely. Yes. And we call those shells energy levels. Yeah, that's exact. Now, some of you are going, wait a minute. I'm not completely convinced that there's still space between the blades. Well, guys, let me show you. There is definitely still space between the blades. I can show you the space between the blades. All right, so guys, how does this work? So it's just like taking and we'll talk about that in a minute. But guys, the idea is this. The light, the strobe light, is flashing at exactly the same speed that the fan is rotating. And so when it's dark, you can't see the blade. When it's illuminated, the blade has had a chance to do a complete revolution, and it appears to your eye as if it's not moving. Now check this out. Ready? Well, because I'm a little bit behind. If I'm a little bit behind the rate at which it's flashing, it'll appear to move backwards. And if I'm a little bit ahead, it'll appear to move forwards. Now guys, check this out. Ready? Guess what we just found? The first harmonic. Here is the second harmonic. Here is the third harmonic. And let's see if I can get the fourth harmonic. I can't get there. I can only get 3 harmonics. It doesn't flash fast enough. You get the idea?
There, but not there.
Exactly. And that's, hold on, did you hear that? Mary's like, it's like it's there, but it's not there. That's electrons, right? It's like it's there as a solid, but we know it's not. It's crazy. But guys, this is exactly how we think of electrons. Do you love it? Go ahead, Ashley. Ooh, good. Yeah, okay, so, hey guys, did you hear the question? Is there something that's fast enough that it can go through? And understand, my rubber bands weren't meant to represent anything. Alpha particles. Remember, those alpha particles passed right through the atom. And that atom is made up of these clouds. So yeah, those alpha particles went right through the cloud. What was it that deflected the alpha particles? Just the nucleus. So there's lots of stuff that's small enough and fast enough that it can fly right through the electron cloud, and the only thing that can disrupt it is the nucleus. Yeah, that's a great question. You guys understand the fan analogy? All right. All right. Now, guys, this gets even a little bit crazier. So here's what we know. Electrons are not particles. Says who? Heisenberg. And then Schrodinger. But Heisenberg said, Bohr, knock it off. You can't do that anymore. They ain't particles. Then along comes Schrodinger and says, okay, let's not worry about where they are and what they're doing. Let's talk about where they will probably be. Let's treat these electrons as if they are large, solid volumes instead of being individual points in space. So guys, picking up from there, Schrodinger gave these volumes names. So you don't need to write this down, but you do need to write down the names. So this idea, and again, don't write this down, this idea of probability treats electrons as if they occupy the whole space, like the fan blades, rather than being points along a path. And guys, he gave these spaces names. He called them electron cloud, and this you want to write down. He called these spaces electron clouds or orbitals. Not orbits, but orbitals. Now guys, here's where this gets even crazier. You ready? Yeah, you are. You just don't know it. This is cool. Okay, guys, so check this out. Are you all caught up with me? Electron clouds are orbitals. That's all you need to write down. You good? Can I go on? Okay, so guys, this is cool. So it turns out that not only are these orbitals more like clouds than they are like orbits, but guess what? A lot of them aren't even spherical. So do you remember how we brought up neon at the beginning of the day, and we said 2 electrons in a little circle and 8 electrons in a bigger circle? Guess what? That is not what neon looks like. You want to see what neon looks like? This is a neon atom. Guys, this is actually what a neon atom looks like. There are 2 electrons that appear to occupy a small sphere around the nucleus. There are 2 more electrons that appear to occupy a larger sphere around the nucleus. And then there are 6 electrons, 2 each, that occupy figure-8 shaped structures, one oriented up and down, one oriented left and right, and one oriented in and out of the plane. That is actually what a neon atom looks like. And guys, here's the thing that's cool. On Thursday, you will not only understand what this is all about, you will also be able to figure out what those pictures look like for every element on the periodic table. Now guys, with that said, and I don't think I'll forget, but remind me, that was going to be the investigation assignment for this unit, because you can probably see that this looks a lot like these, right? And these were extra credit assignments from last year. Now that investigations are gone, guys, on Thursday, I will offer this to you as an extra credit opportunity. I'll show you more about them on Thursday, but you will have the chance for extra credit on Thursday to make a model similar to this. How you doing? You guys good? You guys ready to finally just put the nails in Bohr's coffin and call it quits on Bohr? All right, let's do it. So guys, grab this table. It's in your notes. Did I already title it? Does it have, it does, right? It has Bohr and Schrodinger at the top. Okay, so guys, conceptually, it is time to divorce ourselves from Bohr and fully embrace Schrodinger. Say that again. Get out of my life, Bohr. I'm done with you. Yeah. So, how do we do this? Well, guys, to do this, let's draw some lines in the sand. Why is Bohr incomplete? Why is Schrodinger better? Well, guys, fundamentally, it's this. Bohr was treating an electron like a particle. Heisenberg says you can't because they aren't. So, what did Schrodinger do that was radical? He said, let's not study electrons as particles. Let's study them as waves, as probabilities. See, guys, and the reason that this was practically appropriate is because Bohr's model was just too simple. It oversimplified something that Schrodinger came to find out was actually much more complex. Like the first picture of neon and the second picture of neon. See, guys, so why the simple to the complex? Well, guys, fundamentally it was this. In the early 1900s, Bohr was building his model around the only science that we knew, and that was the science of the heavens and the solar system model. Well, guys, it turns out that atoms are not like little solar systems. Atoms are really better thought of as being a collection of clouds. And guys, unlike the clouds that float around in our skies, these clouds are solid. That's what makes us solid. So in order to think about this, guys, we've got to get rid of this idea of orbits. Orbits work if electrons are particles. But guys, what do we call these clouds that's kind of like orbits? Orbitals. Those are the clouds. See, guys, and the difference is this. If you're going to talk about an orbit, you got to talk about a path. And electrons don't travel in paths. Instead, guys, we don't think of paths. We think of probabilities. And when you think about probabilities, you think about clouds, you think about these solid structures. And that's the magic of the Schrodinger model. Now, guys, this is where we then need to move forward. To fully develop the Schrodinger model, we need to make a jump into the bottom of your page. And to do it, you need to understand this. Guys, when Bohr developed his model, he said there were orbits. N equals 1, N equals 2, N equals 3, right? They just got bigger. So, guys, this idea from Bohr was actually still valuable. He said, let's describe the size of the orbit using a number, an N value. Well, guys, it turns out that things do have size. They just aren't orbits. They're clouds. And so what Schrodinger did was this. He borrowed N from Bohr. But because Schrodinger's models are more complex, you need more variables. So he added 3 more, L, M, and S. So guys, Bohr was wrong. You need more. If all you're worried about is size, 1 variable works. If you're really going to describe what's going on, you need more variables. You need 4. So guys, let me help you make the connection. Ready? How many variables does Schrodinger use? 4. How many heavy black dots are down the left-hand side of the paper? 4. What we're going to do is we're going to talk about what each one of these variables represents. And guys, here's the deal. Don't try to understand any of this. This is just going to be you being a very poorly paid secretary. You're going to write down everything that's on the board. You'll notice that there are blanks. Up on the screen, you're going to see underlines. You're going to fill in the blanks. Forgive me, it's really monkey see, monkey do. Don't try to make sense of any of this. But guys, guess what's going to happen on Thursday? We're going to make sense of this, and you're going to go, you've got to be kidding me. That is really cool. So guys, don't try to understand it, just write it down. You ready? Here we go. Here comes your outline. So guys, these numbers, don't write this down, but these numbers, N, L, M, and S, are what are called quantum numbers. They are the numbers that are necessary to describe the clouds. So what do they mean? Ready? Here you go. The principal quantum number is N. Here's what you need to know about it. That value tells us the size of the cloud. Some clouds are bigger than other clouds. So N tells us the size of the cloud. Now guys, how many different cloud sizes can there be? The answer is, in our universe, 7. For all the elements that we have in our universe, which are collected on our periodic table, there are 7 different cloud sizes. Now guys, how many electrons can go in these spaces or these clouds? Well guys, the answer is what is called the 2n squared rule. Guys, do this with me. Hold on. Don't do this. Do what I'm about to do. All right, so it goes like this, 2n squared rule. So guys, what does that mean? Well, let me show you. Come over here and, oh, my pen doesn't, oh, board's not turned on. Wait for it. That's not helping. There we go. So we're going to go 1, 2, 3, 4, 5, 6, 7. Guys, go ahead and do that down that space that's there next to this. So guys, how many electrons can go in an energy level? Well, these are your N values, 1 through 7. Plug them in for N and do the math. Square first, then multiply by 2. So what is 1 squared? 1 times 2 is 2. So guys, there can be 2 electrons in the first level. You told me you already knew that. Now guys, how many electrons can go in the second level? 2 squared is 4 times 2 is 8. You already knew that, right? Guys, how many electrons can go in the third level? I think some of you thought it was 8. It's not. 3 squared is 9 times 2 is 18. The fourth, 4 squared is 16 is 32. And then 50. 6 squared is 36 times 2 is 72. 7 squared is 49. Is 98. So guys, that's how many electrons can go in these levels. 2, 8, 18, 32, and up from there. That's the 2n squared rule. Got it? All right. So guys, now you need to know three things. As n increases, as n goes up, three things go up as well. The first thing is the size of the cloud. Guys, the second thing that goes up is the energy of the cloud. But guess what? You already knew that. How did you know that? Boom! Good job, Gwen. The flame test lab. Low energy cloud, ground state. High energy cloud, excited state. When the electron falls, it re-radiates the energy as light. That was the flame test lab. And then, guys, the third thing that goes up is the capacity of the cloud. And that is what the 2n squared rule is all about if you want to draw an arrow back. Are you good? Okay, so now guys, here's the thing that's interesting. And you're welcome to do this in your notes. All of this stuff, guys, is the Bohr model of the atom. If the Bohr model of the atom was correct, we could just stop right there. This is all the stuff that Bohr came up with. He thought these things were orbits rather than clouds. But guys, this is as far as Bohr got. So then Heisenberg came along, said, knock it off. Schrodinger picked up the ball, and he said, okay, atoms are more complex. How do we deal with the complexity? And the answer was more variables. And he proposed the next quantum number, which is the sublevel quantum number, which is L. Now, guys, that tells you the shape of the cloud. The L value is the shape. So how many different sublevels can be in an energy level? And the answer is n. Did that follow the notes right? It did. So guys, the number of sublevels in an energy level is n. What does that mean? I'll show you in a second. But guys, before we can talk about what that means, we need to talk about what are the four sublevels. Remember this? S, P, D, and F. The four sublevels, guys, are S, P, D, and F. Do you remember? They are these. S, P, D, and F. These are the sublevels. So, check this out. Ready? What does it mean that the number of sublevels in an energy level is n? Ready? How many energy levels can there be? 1 through what? 7. Now, guys, watch my fingers. You ready? These are energy levels. These are sublevels. In the first energy level, how many sublevels can there be? 1. That's what it means that the number of sublevels in an energy level is n. In the first energy level, 1 sublevel. In the second, there can be 2 sublevels. Third energy level, 3 sublevels. Fourth, 4, and so on. Get the idea? Okay, now here's the question. What are they? First energy level can have 1 sublevel. It's an S. The second energy level can have 2 sublevels, S and P. The third energy level can have 3. You want to guess what they are? S, P, D. The fourth can have 4, S, P, D, F. Now, guys, the fifth energy level can have how many sublevels? 5. What are they? S, P, D, F. It's actually G. Yeah, guys, but here's the thing. We don't have elements complex enough in our universe to need a G sublevel. You can Google them, though. We know what they should look like, because this is all just math, right? We know what they should look like. We just don't have atoms complicated enough to need them. So what do? Well, guys, we say this. In the fifth energy level, we know there could be 5 sublevels, but we just go S, P, D, F. And then in the sixth, could be 6, we just go S, P, D, F. We don't talk about the G's and the H's because they don't really exist. You good? All right. So now, guys, this. Energy levels, sublevels, Now the third quantum number is the orbital quantum number m. And that tells you the orientation. We'll talk more about that on Thursday, but here's what you need to know about orbitals. Guys, what are orbitals? They're the clouds. And how many electrons can go in a cloud? The answer is 2. Guys, orbitals are actually the spaces that are occupied by 2 electrons. And now, guys, we've got a huge problem, and when we're done talking about the problem, we're done with the day and you're going to get your homework done. So, guys, what's the problem? What did you just learn about an orbital? What is in an orbital? How many electrons? 2 paired up. See the problem? Electrons don't want to pair up, do they? Why not? Exactly. They're both negative. They don't, just like protons don't want to pair up in the nucleus, electrons don't want to pair up in orbitals. Now, guys, understand this isn't like the nucleus. What allows protons to pair up? Strong nuclear force, right? Atom bombs, right? Strong nuclear force. Guys, there is not a strong electron force. So, how on earth can electrons pair up if they want to repel because they're both negative? Ready? The answer is really cool. Here's the answer. Guys, you understand that electrons are negative, right? That's the electrical charge. They're both negative. But guess what? They also have magnetic poles. So if you can picture the globe, right? The North Pole and the South Pole, and literally our Earth is like a big old bar magnet. It's got a North Pole, it's got a South Pole, and it spins around the pole. Because guess what? Electrons do as well. Electrons have a North Pole, electrons have a South Pole, and electrons spin around their poles just like the Earth. Now here's what happens. Imagine that my fingers are pointing towards the North Pole. When 2 electrons pair up in an orbital, guess what happens? One of them flips over. And now they are aligned North Pole to South Pole, and that creates attraction that overcomes the repulsion because of their charge. Isn't that crazy? But guys, here's the question. How do we know that, okay, let's see if I can, I've failed at this twice. Let's see if I can do it today. So guys, how do we know that they flip over? Oh boy. So these electrons, my whole body moves. These electrons are spinning around the nucleus, right? When one of them flips over, what then, crap, I failed again. When one of them flips over, what is now true of their direction of rotation? Here they're the same, but if one flips over, they become the opposite, right? It's not because their direction of rotation changed, it's because they're now one is up and one is down. So guys, that's how we talk about this. When we say that electrons pair up because they're North Pole to South Pole, we call that spin. That is what is called or described by the spin quantum number. And the idea is this, and I didn't frankly leave you enough room to write this down, I'm sorry, make it fit. The idea is this. I think I really, oh no, we're okay. So in order for electrons to pair, they must have opposite magnetic, oh I'm hiccuping, opposite magnetic poles. Now guys, here's the way we talk about this as chemistry people. We talk about it as spin up and spin down. But guys, it really doesn't mean one electron is spinning up and the other electron is spinning down. It means their north poles are up and down. And we give those things numerical values. Sorry, I know this is really low on the paper. Plus 1/2 is up and minus 1/2 is down. Now guys, if this whole idea of spin is still weird, check this out. Bless you. This is what we're talking about. Guys, literally, electrons have a north pole and a south pole. And when they meet up,
one electron, remember, paired in an orbital. One electron will be north up, one electron will be north down. So we say we've got a spin up electron and a spin down electron. But really when we say spin up and down, what we mean is they're north or up or down. But the way we know is we can detect their direction of spin. You get the idea? Okay. So guys, now you're thinking to yourself, holy buckets. That was a pantload of stuff. I understand there's strobe lights and fans and electrons are crazy and SPDF, 2n squared rule and what is going on? Well guys, allow this to be your security blanket. Guys, go look at homework assignment number 2. If you can understand and write correct answers to these questions, guys, you are money for Thursday. So question number 1 basically says, why is Bohr wrong? How did Heisenberg prove it? And how did Schrodinger fix it? Question number 2 says, how are electrons like fan blades and where does the analogy fall apart? Question number 3 says, what does the principal quantum number n represent and what increases as n goes up? Now guys, look at the back. You're going to fill in these spaces in tables. Guys, I'd like to do the last question with you. You ready? It says this, what is an orbital? What is an orbital? It's the cloud, right? The orbital is the cloud. How many electrons can go in an orbital? 2. Question number 3. What has to be true of the 2 electrons that are paired in an orbital? What allows them to pair? Their north poles are going in opposite directions. Now guys, this is why I'm doing the last question with you. The 4th, I meant to change the 4th question in the last question and I forgot to. Read what it says. It says, why do we use this term? And that term is spin. So what has to be true of the electrons that occupy the same orbital? They have to have opposite spins. So why do we use this term spin if electrons aren't actually spinning? And you're going, wait a minute. I thought you told me 28 seconds ago electrons are spinning. There's a picture on the board. Why did you tell me that electrons are spinning and now this question seems to indicate they aren't? Because I'm going to just be straight with you. This is the first year where I've ever taught spin to general chemistry students. Frankly, I didn't think your brains could handle it. But I finally decided, forget it. I frankly, for 23 years, I've been lying to students and telling them electrons don't spin, and then I told them I was lying in AP. So, guys, electrons really do spin. So cross out the 4th question. We don't need to answer it because electrons really do spin. So, guys, there you have it. You've got, wow, 15 minutes to get this homework done. I think you will get it done. And then guys, understand when I see you Thursday, we're going to grade this homework and then you're going to keep your homework out. You're going to grab your class notes from today and we're going to have a pretty amazing day together. So get this homework done. I'll post the answers up on the wall. Oh, what else is due on Thursday? Yo, you've got